The autumn air over Tokyo Bay in 1945 still smelled faintly of oil and scorched paint. The war was finished, yet the docks remained crowded, not with ships, but with ghosts. Moored among the twisted remnants of the Imperial Navy, a small delegation of Japanese naval officers stood silently aboard a captured American vessel, its decks broad and immaculate, its hangars vast enough to swallow a destroyer whole. The ship's name, stenciled in crisp white letters across the stern, read USS Essex. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Lieutenant Commander Tadashi Shimizu, a former naval constructor from Kure, rested his gloved hand on the welded bulkhead. The metal was cool and seamless beneath his fingertips, smooth as poured glass. He whispered almost to himself. They built this? In 15 months? An American officer escorting the delegation nodded. From keel to commissioning, he said. All welded. No rivets, no delays. For Shimizu, the words struck harder than defeat itself. 15 months less time than it had taken Japan to refit the battered Shokaku after the Coral Sea. In that moment, he understood something his nation had never truly grasped. Japan had lost the war long before Midway, long before Leyte Gulf. It had lost it in the shipyards. The Japanese had entered the war believing they were master craftsmen of the sea. Their naval architects had studied at Yokosuka and Kure under men who revered precision above all. Each aircraft carrier, from Akagi to Tai-Ho, was hand-built like a temple forged in patience, not speed. Steel plates were riveted by hand, seams caulked and hammered until flawless. Every bulkhead was measured, remeasured, inspected by engineers in white gloves who treated their work as a matter of spiritual honor. The shipyards of Kure and Sasebo operated under a doctrine of monozukuri craftsmanship as virtue. A ship was not a product, it was an offering. This philosophy produced vessels of exquisite design and deadly elegance. The carriers Shokaku and Zuikaku launched aircraft that carved fiery arcs across the Pacific in 1941. The Yamato, a floating citadel of 65,000 tons, symbolized the perfection of that creed built with armor so thick it could defy any known shell. Yet perfection carried a hidden flaw: time. By 1942, American submarines prowled the shipping lanes. Bombs fell on steel mills in Kobe and Osaka. Each lost transport delayed construction. Each destroyed dockyard worker meant another month gone. Japan could not afford patience anymore. Still, its naval establishment clung to it, believing quality would triumph over quantity. Across the ocean, the United States had reached the opposite conclusion. In January 1942, when Admiral Ernest King reviewed the Navy's construction schedule, the picture was bleak. The Pacific Fleet had lost 4 carriers within 6 months. The surviving ones, Enterprise, Saratoga, Hornet, were fighting without relief. New ships were needed, fast. The Navy's Bureau of Ships faced a problem as old as naval architecture itself: time. A traditional riveted carrier required nearly 3 years from keel laying to launch. Even with around-the-clock labor, the sheer number of components, the riveting, the internal bracing, the precision drilling all consumed weeks that America no longer had. That was when a small cadre of engineers proposed something revolutionary and deeply controversial. They would weld the next generation of carriers instead of riveting them. The proposal seemed reckless. Riveting was proven, reliable, and safe. Welding, on the other hand, was still viewed by many naval architects as a dangerous shortcut, prone to brittle fractures and metal fatigue. The memory of cracked Liberty ships still haunted the maritime community. But Henry J. Kaiser's shipyards had shown that, with correct sequencing and material control, welded hulls could be produced not only faster but stronger than riveted ones. The Navy's next class of fleet carriers, designated CV-9 through CV-32, would put that idea to the test. They called it the Essex-class. At the Newport News Shipbuilding and Dry Dock Company in Virginia, work on the first hull began in April 1941, before America had even entered the war. When Pearl Harbor was attacked 8 months later, the half-finished Essex suddenly became the most important construction project in the world. By then, the Navy had quietly implemented a new doctrine of production, one the Japanese delegation after the war would study with stunned disbelief. Instead of building carriers in sequence, the Americans divided the process into modular sections. The hull was broken into massive prefabricated blocks: bow sections, mid-sections, engine compartments, each welded in separate yards, then transported by rail or barge to final assembly. Every joint was electrically fused, not riveted, using flux-covered welding rods and shielded arc techniques that allowed vertical and overhead welds previously thought impossible. What had once required teams of riveters working shoulder to shoulder, hammering thousands of metal pins per day, could now be accomplished by a handful of welders with torches. The time savings were staggering. A pre-war carrier like Yorktown had required nearly 33 months to complete. The Essex took just 15. Subsequent ships in her class, Bunker Hill, Lexington CV-16, Ticonderoga, were launched even faster as the yards perfected the process. By 1944, America was launching a new fleet carrier every 2.5 months. The secret was not merely in the welding itself, but in the system that supported it. The Navy, working with civilian industry, standardized every component from armor plate dimensions to electrical fittings. Shipbuilders at Fall River, Newport News, and the Brooklyn Navy Yard all worked from identical blueprints. Parts were interchangeable between ships, even between different yards. If a deck section for Bennington was delayed in Quincy, a replacement from Brooklyn could be shipped by rail and fitted without modification. This was assembly line thinking applied to seagoing giants. To the Japanese engineers who inspected the Essex-class after the surrender, this was almost incomprehensible. Their shipyards relied on bespoke craftsmanship, each hull shaped slightly differently, each fitting made to match a particular frame. Welding, in their doctrine, was still reserved for secondary reinforcement, never for the main hull. The Americans had made it their foundation. As Shimizu and his fellow officers walked through the silent hangar deck, their footsteps echoed off steel bulkheads that gleamed under fluorescent light. He examined a seam running along the interior wall. The weld line was smooth, consistent, almost artistic in its precision but not handcrafted. It was industrial. He realized that this, too, was a kind of craftsmanship, not of the hand, but of the system. During the war, Japanese naval construction had been slowed not only by bombings and material shortages, but by the very pride of its engineers. A riveted joint required inspection at every stage. Welders needed years of apprenticeship. Quality was ensured by discipline, not automation. When the Kure naval arsenal attempted to accelerate production in 1943, shortcuts led to hull distortions and faulty riveting that delayed completion further. Meanwhile, in places like Newport News and Brooklyn, 17-year-old apprentices were welding flight decks after only 12 weeks of training, guided by jigs, templates, and standardized procedures that ensured near-perfect uniformity. The Americans did not rely on genius, they relied on process. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. By the war's end, 24 Essex-class carriers had entered service. 11 more lay in various stages of completion. No nation in history had built that many ships of such size in such little time. The Japanese delegation measured weld thicknesses, reviewed construction logs, and photographed assembly diagrams with the detached curiosity of men studying an alien civilization. They noted the absence of the old scaffolding structures used for riveting, the streamlined hull sections, the enormous prefabrication sheds where entire hangar decks were welded as self-contained modules before being lifted into place. Each observation felt like a revelation and an indictment. The officers returned to Tokyo that evening in silence. Shimizu wrote in his notebook, "Our shipyards were temples, theirs were factories, and factories won the war." In the months that followed Japan's surrender, the remnants of the Imperial Navy's technical departments found themselves in unfamiliar service not to the emperor, but to reconstruction. The war had erased the fleet, the docks, the steel mills, and much of the confidence that once defined Japanese engineering. Yet, amid the ruins, a quiet revolution began. At the Yokosuka Naval Arsenal, what remained of the Design Bureau was reconstituted under Allied supervision as part of Japan's demilitarized shipbuilding authority. Many of the men who had once overseen the construction of aircraft carriers now wore civilian overalls. Their new assignment was to study and learn from their conquerors. On a damp morning in March 1946, Tadashi Shimizu sat in a makeshift drafting room, surrounded by stacks of photographs, blueprints, and reports compiled during post-war inspections. Across his desk lay an American document, labeled Standard Welding Procedures, Bureau of Ships 1944. It was the same manual used in the construction of the Essex-class carriers. Each page was dense with diagrams, voltage charts, and notations specifying amperage tolerances, bead angles, and material temperatures. The Americans had treated welding not as art, but as math. Shimizu flipped through the manual, stopping at a section titled Stress Distribution in All-Position Welding. It described precisely how welders could fuse steel plates at any angle, vertical, horizontal, or overhead, using flux-coated electrodes that stabilized the arc and prevented oxidation. The text was dry, technical, but to him it read like a revelation. During the war, Japanese welding teams had fought constant problems with overhead seams. Slag would drip downward, contaminating the weld bead and forcing rework. American engineers had solved this through a combination of flux chemistry and electrode shielding, a simple, elegant fix Japan had never mastered. That single innovation, multiplied across thousands of feet of welds, had translated into entire months saved in construction. The more Shimizu studied, the more he realized that the true weapon of the American shipyards had not been welding alone, but documentation. Every shipyard, every shift, every welder followed the same standards, written in language that left nothing to interpretation. In Japan, such precision had been left to the discretion of master craftsmen. Each foreman passed his methods to apprentices through demonstration and repetition, not printed instruction. The result was skill but not uniformity. When air raids or drafts removed those foremen from the line, their knowledge vanished with them. In America, the knowledge lived on paper. Shimizu saw how, at Newport News, a welder could die on Monday, and another, fresh from training, could take his place on Tuesday and continue the line without disruption. The Americans had managed to make their system independent of the individual. To Japanese engineers, this was not just technique, it was philosophy. It turned production into a collective act rather than a personal one. Meanwhile, at the Sasebo Naval Arsenal, similar studies were underway. Captain Minoru Hiraga, cousin of the famed naval architect Yuzuru Hiraga, led a small group examining the industrial logistics behind American shipbuilding. They found that the Essex-class program had relied on more than 60 subcontractors, each responsible for standardized modules, catapult housings, radar masts, hangar doors, elevator systems, all produced under tight coordination with the Navy's Bureau of Ships. The Japanese equivalent had never existed. Each shipyard had built its own fittings, tailored to its own designs. When Sasebo produced the carrier Junyo, its anchor assemblies were incompatible with those built at Kure. Even among ships of the same class, component interchangeability was minimal. By contrast, Essex-class carriers shared up to 80% common components across the entire series. This meant that parts built for Lexington could be installed on Yorktown or Hancock without modification. Such uniformity was unheard of in Japanese shipbuilding, and it explained the Americans' astonishing construction rate. By late 1946, the Yokosuka engineers completed their technical evaluation. Their conclusion was humbling. America's victory at sea had been manufactured not through superior tactics or intelligence, but through industrial symmetry, the ability to turn complexity into repetition. To replicate this system, Japan's post-war shipbuilding industry would need to abandon its centuries-old attachment to artisanal craft and embrace something it once considered vulgar: mass production. Shimizu, now serving as a consultant to the Ministry of Commerce and Industry, helped draft Japan's first standardized welding codes for civilian shipbuilding. The language was directly borrowed from the American Bureau of Ships. Training programs were rewritten to focus on procedure rather than intuition. Apprentices learned amperage and polarity before they learned pride. In workshops once used to build destroyers, young men now welded cargo ships for a peacetime fleet, tankers, ferries, freighters, all based on modular American methods. What had begun as an act of post-war necessity slowly became an identity. By the mid-1950s, the transformation was complete. The same yards that had once produced the Yamato were now turning out commercial tankers at unprecedented speed. Japanese companies like Mitsubishi Heavy Industries and Ishikawa-jima Harima began exporting vessels to Europe and the United States, underbidding Western shipyards by millions of dollars. Foreign observers were astonished. In less than a decade, the nation that had lost its fleet had become the world's fastest shipbuilder. The irony was profound. The lessons learned from the inspection of Essex-class carriers, those symbols of Japan's defeat, became the foundation of its post-war economic miracle. By 1962, Japan had overtaken Britain in annual shipbuilding tonnage. The techniques that once seemed alien, arc welding, modular construction, prefabrication, were now taught as standard engineering practice. In Yokohama and Nagasaki, cranes swung prefabricated hull sections into place with clockwork rhythm. Steel plates glowed under the torchlight not as emblems of war, but of rebirth. One evening in 1964, Tadashi Shimizu, now retired, visited the dockyards at Kobe, where the supertanker Idemitsu Maru was under construction. She would displace over 200,000 tons, 3 times the mass of Yamato, and she was being built in less than 2 years. Standing beneath the towering hull, Shimizu watched a team of young welders seal the final seam of a prefabricated section. Molten arc bathed their faces in orange light. Their movements were swift, standardized, unhesitating. For a moment, he imagined himself again aboard the silent USS Essex, running his fingers along that perfect weld. He smiled faintly. The lesson had been learned. In the years that followed, historians would note that Japan's post-war industrial recovery was rooted as much in humility as in ingenuity. By studying what had once been their enemies' shipbuilding methods, Japanese engineers had dismantled the very mindset that led them to war, the belief that craftsmanship alone could conquer scale. They had replaced it with a quieter philosophy, that mastery lies not in the hand that shapes steel, but in the system that allows 1,000 hands to shape together. The Essex-class carriers remained in service for decades, fighting wars long after their original builders were gone. But their greatest legacy may have been the transformation they inspired a defeated nation, learning from its conqueror, and in doing so, mastering the art of building faster, stronger, and smarter than anyone else in the world. By 1970, the world's largest ship on record, the Nissho Maru, slid into the Pacific, built in record time by Japanese welders using methods first perfected in American wartime yards. And somewhere, in that seamless ribbon of steel stretching across her hull, lay the final echo of a truth first whispered aboard the Essex in 1945. Factories win wars, and sometimes they rebuild nations too. By the dawn of the Cold War, the roar of warplanes had faded, but the hum of shipyards had not. Across both sides of the Pacific, the lessons of the Essex-class lived on not in blueprints, but in philosophy. In the United States, those wartime carriers became a living laboratory for the next era of naval warfare. The USS Essex herself was refitted again and again, first with angled flight decks, then steam catapults, then reinforced, arresting gear to handle jet aircraft. What had been designed for piston-engine planes of 1,943 was now launching jet fighters of the 1,950 seconds. The reason? The underlying modular logic of the Essex design. Every major component, elevators, catapults, radar towers, could be removed, replaced, and modernized without tearing the ship apart. This adaptability, born from the mass production ethos of the war, became the foundation for the next generation, the Forrestal-class supercarriers. For the Americans, welding and modularity had not only won a war, they had bought time to innovate faster than any rival, to project power farther than any empire in history. But in Japan, the Essex-class left a different kind of legacy, quieter, but just as transformative. The engineers who once studied American welding manuals became the architects of a new industrial order. Shipyards that once measured their success in tonnage of warships now measured it in commercial tonnage, oil tankers, cargo carriers, container ships. By 1968, Japan's shipbuilding output surpassed that of the United States, the United Kingdom, and Germany combined. The same meticulous discipline that had once fueled military precision was now fueling economic expansion. And behind it all was that single revelation first made in a silent inspection room aboard an American carrier. Standardization is power. When Japan's Ministry of International Trade and Industry, MITI, introduced its National Quality Control Framework in the early 1962, it was directly inspired by the procedural uniformity observed in American wartime production. The Japanese refined it, softened it, humanized it, and called it Kaizen, continuous improvement. Where the Americans had used standardization to multiply force, the Japanese used it to multiply efficiency. The same idea, seen through two philosophies, one for war, one for peace. In the United States, naval architects continued to push forward. The modular systems that had allowed the Essex-class to be built in 15 months were expanded into the vast, nuclear-powered Nimitz-class supercarriers. Each ship was effectively a floating city over 1,000 compartments, welded from modular blocks built in separate yards, then assembled like puzzle pieces. The lineage was unmistakable. The ghost of the Essex was there in every blueprint, in the standardized wiring harnesses, the interchangeable catapult systems, the procedural weld logs signed in neat Navy block letters. What had once been a desperate wartime shortcut had evolved into the backbone of a superpower's naval might. Meanwhile, in Japan's post-war shipyards, something almost poetic was taking shape. American carriers had once been built to dominate the oceans. Japanese tankers were now being built to connect them. Steel hulls slid down the same slipways that had launched destroyers and cruisers. But now they carried crude oil, cars, and manufactured goods, the lifeblood of global trade. The same methods that had once destroyed Japan's navy were now fueling its economic ascendancy. In 1971, a British naval historian visiting Kure remarked that the rhythm of the Japanese yards reminded him of wartime footage from Brooklyn and Newport News. The tempo, the choreography of cranes and sparks, it was all there. But the music had changed. The Essex-class had done something that neither nation expected. It had created a bridge between two eras of history. For America, it symbolized industrial supremacy, proof that a democracy could outbuild an empire. For Japan, it became a mirror, a lesson in how defeat could be turned into design. Every weld on those ships told a story, of a system that replaced improvisation with discipline, craft with process, chaos with order. That story had crossed the ocean twice, once as a weapon, once as wisdom. In 1975, the last active Essex-class carrier, the USS Lexington, was retired after more than 30 years of service. She had launched biplanes, then jets, then training squadrons, a ship reborn through decades of technological change. A few months later, across the Pacific, the Yamato Museum opened in Kure. Among its displays stood a small exhibit on post-war reconstruction. One of the panels showed photographs of Japanese engineers inspecting an American carrier in 1945. Beneath the images was a single caption: "From defeat, we learned construction." It was a quiet acknowledgement, not of humiliation, but of transformation. By the end of the 20th century, the world's shipyards, whether in Nagasaki, Busan, or Pascagoula, all followed the same principles first proven on the Essex line: modularity, procedural welding, parallel production. The very blueprint of modern industry had been written in those war years, and though the guns of that era had long fallen silent, The weld lines remained running unbroken through decades of steel, connecting the past to the present, the conqueror to the conquered. Each seam a record of heat, pressure, and purpose. Each spark a reminder that power, once unleashed for war, can be refined into something enduring. As historian John Parshall later wrote, "The Essex-class carriers were not just weapons of war, they were factories of learning. And in their wake, both America and Japan built not just ships, but futures." In the end, the story of the Essex-class was not about ships or steel, but about systems. One nation forged them to win a war. Another studied them to rebuild its soul. And somewhere between the two, between the hammer and the torch, lies the quiet truth of the 20th century. The strongest empires are not those that build the most ships, but those that learn the fastest from the ones that came before. When the Cold War dawned, America's factories faced a paradox. The war that had once demanded total mobilization was over, but the world that followed required permanent readiness. The Navy's Bureau of Ships, which had designed the Essex-class, evolved into the Naval Ship Systems Command. Many of its wartime engineers were now grey-haired bureaucrats or private consultants, but their wartime notebooks became the basis of a new doctrine: continuous modernization through modularity. They had learned a crucial lesson. No weapon could remain relevant if it couldn't evolve faster than the threat. This idea, born from the interchangeable modules of the Essex, became the foundation of Cold War naval engineering. Every new American ship, from destroyers to submarines, was designed with replaceable core systems. Radars, engines, missile silos, all built to be removed, upgraded, and reinstalled without rebuilding the hull. It was industrial Darwinism, written in steel. When the nuclear-powered USS Enterprise was launched in 1960, it owed its existence to this same logic. Her systems were compartmentalized into 23 replaceable modules, a concept directly inherited from Essex-class production methodology. In wartime, modularity had built ships faster. In peace, it built them smarter. Across the Pacific, Japan's metamorphosis was even more profound. The engineers who had once studied the Essex's welded seams now applied those principles to peacetime industry. Shipyards became laboratories for mass production and process control. The country's post-war miracle was, in essence, a translation project taking the cold, procedural rigor of American manufacturing and infusing it with a human rhythm. In 1950, a former naval engineer named Taiichi Ono joined Toyota Motor Corporation. He had never built a car in his life, but he had studied American shipyard diagrams distributed under the Allied occupation. What he saw was structure, flow rhythm. He recognized that what allowed the Essex to be built in 15 months was not size or manpower, but the choreography of parts and people. Ono began mapping out what would become the Toyota production system, later known as lean manufacturing. Its essence was borrowed from the Essex-class philosophy: eliminate waste, standardize process, and create systems that learn from themselves. Even the concept of just-in-time manufacturing mirrored the Essex shipyard's wartime approach. During carrier production, American dockyards had synchronized the delivery of prefabricated modules so tightly that hull sections arrived precisely when cranes were ready to install them, not a moment sooner or later. It was the same logic that Toyota would later perfect in the 1,960 seconds with automobile assembly lines. The tools of war had been turned into tools of efficiency. In 1955, Japan's Ministry of International Trade and Industry established a new committee to study American industrial techniques for domestic adoption. Among its early case studies were two programs: the Boeing B-29 production model and the Essex-class shipbuilding process. The Essex program had generated mountains of paperwork diagrams, weld schedules, inspection reports. To the Americans, it was a bureaucratic necessity. To the Japanese, it was revelation. They realized that the true innovation wasn't welding or steel, it was information flow. Every step in American wartime production had been recorded, quantified, and fed back into improvement loops. It was primitive data science feedback before computers. Japan's engineers began to build their own version of this data loop. Factory reports, error tracking, daily feedback meetings, all tools designed to replicate what American shipyards had done with paper and pencil. Within 2 decades, this system evolved into what the world came to know as Total Quality Management, TQM, and Kaizen. These weren't Japanese inventions alone, they were transplants, refined with precision and patience. In a sense, Japan had taken the mechanical heart of the Essex and taught it to beat. The deeper irony of history is that while Japan perfected the methods of the Essex-class to rebuild its economy, the United States, the original creator, gradually drifted away from them. By the late 1972, American heavy industry had begun to decentralize. Shipbuilding contracts were fragmented, oversight diluted, and the collective discipline that once defined wartime production eroded under bureaucracy and corporate competition. Japanese yards, meanwhile, operated like orchestras, every worker, welder, and inspector following a unified rhythm. At Mitsubishi's Koyagi yard, a single ship could be assembled from hundreds of prefabricated blocks shipped from small regional factories, a structure nearly identical to the Essex system, but executed with the precision of a Swiss watch. When American observers toured Japanese shipyards in the early 1980s, one of them wrote, "They are building ships the way we once built Victory." It was a quiet, melancholy realization. The system that had defeated Japan had now been perfected by Japan and forgotten by its inventors. By the end of the 20th century, nearly every industrial nation, South Korea, China, Germany, and Singapore, was operating on derivatives of the Essex logic. The idea that complex machines could be assembled from standardized, interchangeable parts had become the bedrock of globalization itself. The container ships that carried goods across oceans were built using block construction methods first developed for wartime carriers. The container ports that handled them from Rotterdam to Yokohama were designed for continuous throughput, echoing the unbroken pace of wartime dockyards. Even in the world of technology, echoes of the Essex philosophy were everywhere. When engineers at IBM developed the first modular mainframe computers in the 1960s, they described their design process in terms borrowed from naval architecture: modules, hulls, sections. The same language reappeared decades later in software design in the term modular programming. The Essex-class had done more than launch planes. It had launched an idea that complexity could be mastered not through genius, but through structure. Behind the machinery, however, there was something deeper, a transformation of mindset. Before the war, both America and Japan had worshipped the myth of the individual craftsman, the shipwright who shaped wood by instinct, the engineer who designed by flair. It proved that systems, not heroes, built empires. That precision could be democratic. That genius could be distributed across 1,000 ordinary hands, so long as those hands worked to the same rhythm. In post-war Japan, this realization had a profound cultural impact. The country that once glorified samurai valor now glorified factory discipline. Newspapers in the 1960s ran profiles not of generals or pilots, but of welders and line supervisors. Productivity became patriotism, and where wartime slogans once praised sacrifice, post-war posters praised standard. One line, one product, one standard. Read a Mitsubishi shipyard banner in 1958. Consistency is strength. It was the Essex creed, reborn in Japanese prose. There is a haunting beauty in the arc of this story. The Essex-class was built for destruction, yet in its design lay the seeds of reconstruction. It was the ultimate paradox of modern history. The tools that won the war also built the peace. When the war ended, Japan had no navy, no army, no aircraft industry. But it had its engineers' men who remembered the lines of the Essex hull, the way her welds ran like veins beneath her deck, and they remembered that her power had not come from weapons, but from organization. So they reorganized themselves. They took the mechanical logic of the Essex and translated it into a moral one, that perfection was not a matter of glory, but of improvement, endless, humble, methodical improvement. In a strange way, Japan's post-war industrial ethics became the spiritual opposite of its wartime culture. Where once it believed that devotion could overcome design, it now believed that design was devotion. The spark that once lit furnaces for war now illuminated blueprints for ships, cars, cameras, and microchips. The torch of the welder became a symbol of creation. Today, when a massive ship glides down a dry dock in Busan or Nagasaki, it's hard to imagine that its DNA traces back to the desperate improvisations of wartime America. Yet the connection is unbroken. Modern shipyards still rely on the same principles: prefabricated modules, standardized weld protocols, shared documentation systems, distributed manufacturing networks, even the digital tools that govern today's construction, computer-aided design, digital twins, just-in-time logistics are refinements of the same dream that animated the Essex-class, to make complexity controllable and control reproducible. But the lesson runs deeper than technology. It reminds us that power is not just built with steel and fuel, but with structure, discipline, and humility. The Essex-class was proof that a nation's strength lies not in its resources, but in its ability to organize them. And the miracle of Japan's recovery proved the same truth in reverse: that a nation can lose everything, its cities, its pride, its fleet, and still rebuild, if it learns faster than it forgets. In 1983, the USS Lexington was turned into a museum ship in Corpus Christi, Texas. Her decks are quiet now. Children walk where sailors once ran. Her hangars echo not with the sound of aircraft engines, but with the voices of tourists marveling at the enormity of what human hands once built. Half a world away, in Yokosuka, Japan, the last of the old wartime shipbuilders are gone. Their apprentices now design ships entirely, on computers, their welders guided by robotic arms and precision sensors. Yet, in every Japanese shipyard, there remains a ritual. Before the first arc is struck, workers bow slightly to the hull, a silent gesture of respect for the craft. Most don't know where that tradition began, but if you trace it far enough back through decades of peace, war, and reconstruction, it leads to that moment in 1945, when Japanese engineers stood aboard an American carrier, running their hands across a perfect seam of steel, and realized that defeat could be instruction. Every generation inherits tools from the one before, but only a few inherit systems. The Essex-class was one of them. It taught that victory is not a moment, it's a method, that the real battle is not against enemies, but against inefficiency, pride, and inertia, and that the true genius of engineering lies not in invention, but in coordination. Japan learned these lessons in the ruins. America learned them in triumph. Both built empires from them, and perhaps that's why, long after the last carrier was decommissioned, the Essex still matters, because behind its rivets and welds lies a universal truth that civilization itself is the greatest machine we ever built. And, like the Essex, it endures only when its parts, people, institutions, nations work in harmony. In the end, the Essex-class was not merely a fleet of ships. It was a manual written in fire, translated in humility, and passed between enemies who became students of each other. It taught America how to organize, and Japan how to rebuild. And as long as we remember that systems, not pride, build the future, the welds that once divided nations will continue to hold the world together. In every photo of those wartime yards, there's a face half hidden by sparks, a welder's mask, a riveter's goggles, a shipfitter's cap turned backward. They weren't soldiers, but their battlefield was measured in deadlines and tonnage. Each man or woman on the line welded about 30 feet of steel a day. Multiply that by the thousands of workers at Newport News, Brooklyn, and Quincy, and you get a symphony of motion, an orchestra of flame and sweat that played not music, but momentum. Few of them ever saw the ocean, yet every plane that took off from an Essex deck, every convoy saved by her air cover, began with those hands. In Japan, the same kind of hands would later rebuild their nation not as soldiers, but as engineers, craftsmen, factory workers. They took what they had seen, that endless rhythm of production, and turned it into the heartbeat of reconstruction. History remembers the admirals, but it is the welders who built the world they commanded. Even after the war, the Essex carriers refused to fade quietly. They were refitted, rearmed, repurposed. They launched the first jet fighters from American decks, ferried helicopters to Korea, and carried relief supplies to disaster zones. Each refit told the same story: adaptability. The Essex design had been so flexible, so forward-thinking, that even as the weapons changed, the ship remained relevant. It was almost poetic. The system built to survive production bottlenecks became a design that survived history itself. In time, many were sold for scrap, their plates melted down, their decks cut apart. But even in death, they served another purpose. The recycled steel from those ships was used in construction projects across the United States bridges, water towers, grain silos. Pieces of the Essex, Bunker Hill, and Ticonderoga likely still stand somewhere in small towns today, rusting quietly under the sun. The warships that once carried the weight of a nation's hope became part of its landscape, invisible monuments to endurance. In 1953, a small delegation of Japanese shipbuilding engineers visited the Brooklyn Navy Yard. Officially, it was part of a post-war industrial exchange program. Unofficially, it was a pilgrimage. They walked through the now peaceful docks where Essex carriers had once stood like titans, blocking out the sky. An American guide pointed to a welding station, the same type used in 1944, and explained how crews had rotated every 6 hours to keep production constant. One of the Japanese visitors, a grey-haired man named Shimizu, remained silent for a long time. He had seen those same welds 8 years earlier, in the aftermath of Japan's surrender. He had studied them, memorized them, and brought their lessons home. Now, standing on the very ground where those ships had been born, he felt something shift. The lines of defeat and victory had blurred. What remained was respect, the craftsman's reverence for another craftsman's work. As they left, Shimizu turned to his interpreter and said softly, "In war, we learned their power. In peace, we learned their method. Perhaps that is balance. Every ship carries echoes, sounds trapped in metal." For years after their retirement, crewmen claimed they could still hear the clang of hammers in the hull, as though the ship remembered its own making. Maybe it's just imagination, or maybe it's something deeper, the idea that creation leaves an imprint, even after the creators are gone. The Essex-class, in that sense, was alive, not because it sailed, but because its spirit, its system continued to build, long after its purpose had changed. That spirit crossed oceans, it reshaped economies, it rewrote how humanity thought about making things. And somewhere between the whine of an arc torch and the hum of a modern factory robot, that same rhythm still beats the rhythm that once built carriers in 15 months and nations in a generation. By the late 20th century, Japan and America had become allies, their shipyards no longer racing to outbuild each other, but to outthink the world together. Joint research programs, shared technology, student exchanges, the children of welders now designing satellites and spacecraft. The same discipline that once welded armor plate was now used to weld rocket fuselages. The Essex philosophy had escaped the sea entirely. In 1992, at the Mitsubishi Heavy Industries shipyard in Nagasaki, an old engineer named Tanaka addressed a group of young apprentices on their first day. He began his welcome speech with a story few expected, the story of the Essex-class carriers. He told them how, decades earlier, his mentors had studied those American ships after the war, tracing the welds, copying the standards, and learning humility from defeat. Then he said something that the apprentices never forgot. "You are not just building ships. You are continuing a conversation, one that began in war and must end in peace." Steel remembers heat. Every weld tells a story of pressure, of resistance, of fusion. It is born in violence, yet shaped by precision, a contradiction that mirrors the century it defined. The Essex-class was that contradiction made visible, built to destroy, yet destined to teach. Its legacy is not in tonnage or battles won, but in the method it left behind, a method that made mass production a language of cooperation instead of conflict. For America, the Essex was proof of what unity could accomplish. For Japan, it was a lesson in what humility could rebuild. Together, those lessons became the foundation of a new global order, one where nations competed not in arms, but in ideas, efficiency, and innovation. The war had ended, the work had not. Imagine, now, the shipyard at night. The cranes stand silent, the water is still. Somewhere, a single torch flares a bright blue arc against the dark. The man holding it could be anyone, American, Japanese, Korean, it doesn't matter. He bends over a seam of steel, steady and focused, guided by standards written long before he was born. That weld will outlive him. It will hold ships, together through storm and distance, unseen but essential. In that moment, he joins a lineage not of warriors, but of builders. The same lineage that began when engineers, enemies once, discovered that the true strength of a nation lies not in the fire of destruction, but in the precision of creation. And if you listen closely, through the hiss of the torch and the crackle of the arc, you can almost hear the echo, the sound of the first Essex being built, and the promise it left behind. Build well enough, and even your enemy will learn from you. The Essex-class ended the age of craftsmanship and began the age of systems. But in the end, it also proved that behind every system are hands human, fragile, determined hands. Hands that once built carriers for war and later built ships for peace. The world they left us is welded from both. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.